Okay, good day. This is Math 130, Intro to Statistics. I'm Professor McCulley. This is Lesson 17, Sampling Distributions and the Central Limit Theorem. So let's get right to it. Today we're going to find a sampling distribution and verify its properties. We're going to interpret the Central Limit Theorem, and then we are going to apply the Central Limit Theorem to find the probability of a sample mean. So the first thing we need to do is define what a sampling distribution is. So the first thing off is a sampling distribution is a probability distribution. So when you're done, when they say find a sampling distribution, you'll have a probability distribution and all the characteristics of that, of a sample statistic that is formed when sample size n are repeatedly taken from a population. So we're going to do an example of that over a small population and a small sample size because these sampling distributions get fairly big and complex fairly quickly. If the sample statistic is the sample mean, then the distribution is the sampling distribution of the sampling means. Every sample statistic has a sampling distribution. Often, sampling distributions are taken because they are easier to perform than to get a census. A census is usually fairly large. And for certain statistics which target an entire population. So some statistics target the entire population. On the next slide, we'll talk about what are good statistics and what are not so good for sampling distribution. And sampling is always taken with replacement. So each draw is an independent event. And you know, if you don't have replacement, the probability each time changes. So independence is a very important part of this. Statistics that target the entire population where sampling distribution may be useful is mean, variance, and proportion. Statistics that do not target the entire population, sampling distributions would not be useful. So median probably wouldn't be useful with a sampling distribution. Range and standard deviation are probably not going to be helpful when you're talking about sampling distributions. Properties of sampling distribution of sample means. So the mean of the sample means, which here we can see that this is the mean and this is sample means. So this is the mean of those sample means is equal to the population mean, which is good. And then the standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size. And so if we can find the standard deviation divided by the square root of sample size, we will get the standard deviation of the sample means. This particular statistic is kind of important. The standard deviation of the sample means of the sample is called the standard error of the mean. And so we will be using that to solve some problems here later on. So the first thing we want to do is perform a sampling distribution. And so we have the heights of 4 swimmers. And so in this particular instance, our 4 swimmers are our population. The swimmers are given in inches. Assume that the sample sizes of 2 are randomly selected with replacement. Their heights are 72 inches, 73 inches, 75 inches, and 76 inches, with a global mean of the 4 heights is going to be 74. So we're going to conduct a sampling distribution of the mean. And so the first thing that we want to do is we want to talk about our samples. We want to talk about the mean of those samples, which again, X bar, and we'll have some more, and there's a lot of samples, as you'll see, and so there'll be a lot of means of those X bars. Okay, so we can we're going to do a list of all of the possible combinations of choosing 2 from this sample, or from this global group, this population. And so since we're doing with replacement, I could pick 72 in the first one, put it back in, and pick 72 again. And that will have that sample has a mean of 72. All right. So now we want to go through and think about all of the possible combinations that we could get by picking 2 of these while also replacing. So we could go 72 on the first one and 73 on the second one. That has a mean of 72.5. We could pick a 72 on the first one and then pick a 75 on the second one, and that will have a mean of 73.5. We could pick a 72 and a 76. That will have a mean of 74. We could pick a 73 and then a 72. That will have a mean of 72.5. We could pick a 73 and then a 73 again. That'll have a mean of 73. We could pick a 73 and then a 75, and that'll have a mean of 74. We could pick a 73 and then a 76, and that'll have a mean of 74.5. We could pick a 75 and a 72, that'll have a mean of 73.5. We could pick a 75 and a 73, that'll be that'll have a mean of 74. We could pick a 75 and then a 75 again, that'll have a mean of 75. We could pick a 75, and then a 76, and that'll have a mean of 75.5. We could pick a 76 and a 72, which will have a mean of 74. We can pick a 76 and a 73. That'll have a mean of 74.5. And then we could pick a 76 and a 75. That'll have a mean of 75.5. And then we could have a 76 and a 76, which will give me a mean of 76. All right, so our sampling distribution is a probability distribution. And so what we're going to do is we are going to count all of these, how frequent each of these means occur. All right. And so here's what we're going to do. We're going to have another, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need another table here. And let's make it a custom table. I need just 2 columns. And I need 10. Let's type that in there. All right, so I don't need everything. I don't need it to be quite this big, I don't think. Come on, let me have the whole column. There we go. I'll bring this over. All right, so here are our means, and here is the probability. And so this is going to be our probability distribution of those means. All right, and remember, probability distribution is just the number of occurrences over the total number of possibilities. So here are my samples: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 different samples. All right. So the smallest sample that occurs is a 72. Our sample mean is a 72. And so that occurs once out of the 16 possibilities. The next sample mean is 72 and a half. Oops, that didn't come out quite right. 72 and a half. And that occurred twice, so 2 out of 16. And again, you wouldn't leave 2 out of 16 in your final answer, but just for the sake of argument. 73, there was 173, so 1 out of 16. And then there are 73 and a half. And there were 2 73 and a halves. If you go through, and again, this list, look. Let's see, 73 and a half, there's 1, and then there's a 73 and a half there, and that's it. So you see what I'm talking about. 74, well, there were actually 4 74s in the list. And then 74 and a half, there were only 2 in our list. 75, there was 175 in our list. 75.5, there were 2 in our list. And then 76s, there was only 1 of those in our list. And again, we're just counting up the numbers, so all of these probabilities, I go 1 plus 2 is 3, plus 1 is 4, plus 2 is 6, plus 4 is 10, plus 2 is 12, plus 1 is 13, plus 2 is 15, plus 1 is 16. If I add up all of the probabilities, I get 1, so this is a probability distribution. All right, so Again, just to reiterate, this number is the frequency that this mean came up in our list of possibilities. And then this is the total number of different sample means that we got, or different samples that we could get. And that's how I get those probabilities. All right, so just a couple of quick notes just to review. The mean of the sampling distribution is equal to the mean of the population. And to find the standard deviation of the population, we need to find the sum of squares. So here's what we want to do. The population standard deviation has an equation. Well, if we find the variance, so the variance is the standard deviation squared, which is the sum of the individual x values divided by the mean squared all over the population mean. All right, so if I make this calculation right here, um, it's going to be, since our population, oops, where do we go? Population. 72, 73, 75, and 76, and our mean is 74. So to make that summation calculation, I'm going to go 72 minus 74 quantity squared plus 73 minus 74 quantity squared plus 75 minus 74 quantity squared plus 76 minus 74 quantity squared. Now that is just the sum, and there are 4 elements in the population, 72, 73, 75, and 76. And so this variance comes out to be 2.5, or 2.5. And so if we take the square root of that, we get this standard deviation of the population to be 1.5811. Now, if we want to find the standard deviation of the sample means, we recall from this particular slide here, the standard error, it's just the standard deviation divided by the square root. And so our square root of the number of the sample size. So if I want to find that standard deviation there, it's going to be this 1.5811 divided by the square root. Our sample size is 2 because I took 2 elements from each of those samples. That's where I get the 2 from. And so that calculation, if you grabbed your graphing calculator and did that, you would get 1.1180. And so that is the standard deviation of these sample means. And we can verify that that's true with our graphing calculator. If I hit the stat, let's clear out the list here. So we want to clear lists, and we need to clear out 2 lists here. So L1 and L2. If we clear that out, and then if I hit statistics here, I hit edit, and I'm just going to enter the data from that sampling distribution. So 72, 72.5, 73, 73.5, 74, 74.5, 75, 75.5, and then 76. And then the probability is going to be our frequency list. So 1 over 16, 2 over 16, 1 over 16, 2 over 16, and then the 74 had a 4 over 16. And then the next one was a 2 over 16, and then a 1 over 16. Oops, that should be 1 over 16. I don't really mess it up if I left 16 there. And then it was 2 over 16, and then a 1 over 16 again. And so again, what am I doing here? I'm verifying that this sampling distribution has this standard deviation. So if I go second and I go, I just hit stat. I'm sorry, I shouldn't hit second. Just hit stat. Go over to calculate. Go first variable stats. You want L1, and then your frequency list needs to be L2. If you hit enter, you can see that the standard deviation of the sample means is the 1.1180, which is what I got right here. All right. All right, moving on. The central limit, if samples of size n are greater than 30, so 30 elements are drawn from any population with a mean of u and a standard deviation of sigma there, then the sampling distribution of the sample means approximates a normal distribution. The greater the sample size, the better the approximation. Or if the population itself is known to be normally distributed. So you don't need a sample size of 30 if they tell you in advance that the sample is normally, or the population is normally distributed. Then the sampling distribution of sample means is normally distributed for any sample size n. In either case, the sampling distribution of sample means has a mean equal to the population mean. So the sample distribution has the same mean as the mean of the entire population. So then we can say that the sampling distribution of the sample means has a variance equal to 1 over n times the variance of the population. And then the standard deviation is equal to that standard error equation, which we had before. So, probability and the central limit theorem. In a previous lesson, we learned how to find the probability of a random variable x will lie in a given interval of values. That's what we did in the last couple lessons. In a similar manner, we can find the probability that a sample mean, x bar, will lie in an interval of the sampling distribution. So normally, to transform that to a z-score, we would use the value minus the mean, which would be the sampling mean minus the mean of the sampling means, divided by the standard error, or whatever that is, divided by, and since this is equal to the population mean, we can just substitute that in, and then the square root of the number of elements in the sample. So we could do all that work if we wanted to, but as a practical application, we can use that normal CDF function that we used in the last couple lessons and replace the standard deviation with a standard error. That's all we would have to do. The heights of high school students are normally distributed with an average of 62.3 inches with a standard deviation of 3.5 inches. If 20 students were chosen at random, what is the probability that A, their mean heights lie between 59 and 62 inches, and their mean heights are less than 65 inches? Okay, so they're asking for probability. That should be CDF. But they're saying if 20 students are chosen at random, what is the probability that the mean heights, not that the heights of these students, that the mean of these heights lie between those two? And so since they're asking that, now we're talking about the central limit theorem. And so for us to make this calculation, the first thing that we have to do is we have to, number one, come on, give me my pen back. Number one, we need to calculate the standard error. And so the standard error is, the x bar there is equal to the standard deviation by the square root of the number of, come on, let's do this right, x bar standard deviation over the square root of the sample size n. Now, we absolutely need to know the fact that this is normally distributed because our sample size is only 20. So if we go back to that central limit theorem, we can do we can use this central limit theorem if the population is normally distributed or if the sample size is greater than 30. Either one counts. So in this case, since it is normally distributed, our sample size of 20 still allows us to do that. So in this particular case, we're going to go 3.5 and we're going to divide that by the square root of our sample size, which is 20. I calculated this off to the side already, and it comes out to be 0.7826. That is our standard error. All right, so What is the probability? So part 2 is, this is still 1. So the next thing we're going to do is use the normal CDF function with the standard error. All right, so our answer here is going to be normal CDF, and then it's lower bound 59, upper bound 62, the mean value 62.3, and then the standard error, not the standard deviation for this one, 78.2 or 0.7826. And so if I grab my graphing calculator, 59, 62, 62.3 is our mean, and then 0.7826. If I hit enter, we paste that in, and I'll get 0.03507. So 0.3507. That is the probability that the mean heights lie between that, or 35.07% chance that they're going to lie in between those. Where the mean heights are less than 65 inches, well, we've already calculated the standard error. So number 2, we're just going to again use the normal CDF. But this case, we'll put in our negative 10,000 because we just want it to be less than 65 inches. Our upper bound is going to be 65 inches. And then we'll keep our global mean, which is our mean of the sampling distribution, and then our standard error, 78.26. And so I'm going to grab my graphing calculator. We're going to go second entry. Let's see here. Come on. I want to change all of this stuff, I don't think. So negative 10. Let's do an insert. 0, 0, 0, 0. And then we want to be 65. That's what I wrote there. 65. And then everything else stays the same. So that's good. Hit enter. And so there is a 99.97% chance, or a 0.9997 probability that all 20 of those students will lie less than 65 inches. Okay, so another example here. The average credit card debt held by undergraduates is normally distributed with a mean of $3,173 and a standard deviation of $1,120. What is the probability that a randomly selected undergraduate who's a credit card holder has a credit card balance less than 72 or $207 or $2,700? I'm sorry. Well, since this one isn't talking about a sample, it's just talking about a single student, we're going to just use the regular, number 1, since just one student, we're going to actually use the standard deviation. All right. And so this one is just going to be our normal CDF. And our lower bound of debt is going to be negative 10,000 again. Our upper bound is 2,700. Our mean is 3,173. And then our standard deviation is 1,120. And so again, I think it's, if I do my distributive normal distribution, negative 10,000. And then the upper bound is 2,700. Our global mean 3,173. Standard deviation 1,120. Hit enter there. You got a 33% chance, 0.336 or 33.6% chance that that student will have a debt less than $2,700. Now, the second question, number 2, it says if 25 graduates whose credit card holders are randomly selected, what is the probability that their mean credit card balance is less than $2,700? So now they're saying, okay, if I pick 27 students and I actually found out what their credit card debt was and I averaged it, what is the probability that that mean will be less than $2,700? Now, because this is a sample mean, now we're going to have to calculate the standard error. Which in this case is going to be that standard error, and again, it's the standard deviation divided by the square root of the number of elements in these in the sample. And so in this case, it is 1120 over the square root of 25. And I've calculated that already to be 244. And so notice it makes it a little bit smaller there. Or it makes the number that I'm going to plug in smaller. And so now normal CDF, and it's going to be 10, again, negative 10,000 is that lower limit. Our upper limit is still 2,700, and our global mean is still 3170 because the global mean is equal to the mean of the sample means. But we're going to shrink our standard deviation using the standard error by quite a bit. And so that's going to shrink that up quite a bit there. And so I am just going to, again, hit second entry and pull that up. And we're going to change this thing to 22224. And then we'll delete that last 0 and hit enter there. And we get 0.0174. That looks good. So 0.0174, or a 1.74% chance. So it says interpret the probabilities. Well, let's talk about them. So 3, picking a single student at random and getting a credit card debt of less than $2,700 is not unusual. 33.6%. But taking T-A-K-I-N-G, a mean of 25 students debt and getting less than $2,700 is very unusual. Not very, just unusual. At only 1.74% chance of getting that. Well, that's all I got for today, folks. So, the Marvel fun fact of the day, the sound of Yellow Jacket's blaster fire is the same sound that was used as the blaster fire of the AT-AT walkers from Star Wars The Empire Strikes Back. This is Disney synergy at its best, since Disney owns all of that stuff now. They will be our corporate masters someday. I'll leave you with that dark fact. Bye, guys.